Assalamualaikum warahmatullahi wabarakatuh. So my name is FARHAD SYED ILHAM. I'm from UR6523007. So today I'll be presenting my continuous alternative assessment number 1. So let's get started. So question 1. What is an ideal op-amp? So an ideal op-amp is an amplifier which meet the following criteria. So it has a infinite voltage gain, infinite bandwidth, infinite input impedance, zero output impedance, zero input bias current. So as you can see from the diagram, so this diagram is an ideal operational amplifier diagram. So we have so it meets the criteria. So the input impedance is infinite, and the output impedance is 0. So the voltage gain, we have to calculate. So which should be infinite too. So for zero input bias current, so input bias current should be here, I1 and I2. So it should be 0 too, since the input impedance is infinite. So it should be 0. So will the voltage that will come through here will also be 0. So next, distinguish the property of an LM7741 to an ideal op-amp. So LM741 is a practical operational amplifier. So this is the difference between a ideal operational amplifier and a practical operational amplifier. So an ideal operational amplifier will have infinite voltage gain, but for a practical operational amplifier, we can only achieve a high voltage gain, which is around 1 million gain. So a practical operational amplifier cannot have the same value as an ideal. It's impossible to have the same value as an ideal operational amplifier. So infinite input impedance. So for a practical operational amplifier, we can only have very high input impedance. So as I said, it's impossible to get infinite. So zero output resistance, so we will get very low output impedance. So noise, so an ideal operational amplifier will have no noise. For a practical operational amplifier, there will always be noise because it's practical, so noise is unavoidable. So another statement is zero voltage for ideal operational amplifier. Here we get 0, but for a practical operational amplifier we will get nearly 0. So it's not 0, but it's nearly 0. So we can state that it's 0 too, but actually it has a value of 0.0 microvolt, something like that. So question 2, show an operational amplifier with input voltage step and the output. So this is the operational amplifier circuit for slew rate that I created. So this is the voltage step. So it's a negative feedback operational amplifier. So this is the output slew rate of the circuit. Since the circuit does not have a RF, so it should not have any gain. So the maximum will also be 5 volts too, like the input. So since here is 5 volts, the maximum, so here will also be 5 volts. So next, so what is a slew rate? Slew rate is the maximum rate of change of the output voltage. So maximum rate of change, so rate of change meaning it will have something to do with time. So the voltage and time, so this is the slew rate. We will have the how fast the voltage can increase by time. So as you can see, slew rate for here, so slew rate for output and input should be the same value of time. So like here is 9.6 milliseconds to reach to the peak, and it will need around, yeah, so So you need that much to increase from 0 to 5 volts. So as you can see, we will use around 5 microseconds. So to get the slew rate, we just need to take the maximum positive voltage which is 5 volts, and minus with the negative maximum voltage which is 0. So we get 5 minus 0 over with 9.600 9.6052 milliseconds minus with 9.6000 microsecond milliseconds, so we should get 5 microseconds. So we get 5 over 5 microseconds, we should get around 1 volt over 1 microsecond over a microsecond. So that is the slew rate for the circuit that I have created. So is the slew rate important? So the slew rate is important because it shows how fast the operational amplifier can respond. So if you're given two operational amplifiers and you don't have anything else but the waveform, so you can see how fast or how fast the rate of change of the output voltage by using the slew rate. So the higher the slew rate, the better the operational amplifier. But sometimes it does not. Sometimes we want lower power consumption, so maybe a higher slew rate is not better for that situation, because higher slew rate will also means that it will use more power consumption. So question 3, for inverting operation amplifier, where is the virtual ground? So the virtual ground will be here. The virtual ground is here. So the property of virtual ground property is that the voltage at the virtual ground is not actually 0. It has a value which is a small value that is close to 0, so we assume that is 0. So like I said, it should be around 0.000 microvolts, so which is very close to 0. So the next property of a virtual ground is a virtual ground is not directly connected to a ground. So like this one, it is directly connected to ground. So virtual, it means that it's not connected, it's virtually, so it's almost 0, so it is known as virtual. So the next is closed loop voltage gain and input impedance. So input impedance for this circuit should be, because both of the voltage inputs are 0, the input impedance should be the value of R1. So that is the input impedance. So the closed loop voltage gain, so for the closed loop gain, we can create a formula based on the values. So this is the formula for the closed loop gain. So I simplified the circuit to make it more easier to understand, so we can see the flow of the current. So we should get I1 is equal to IRin is equal to IRF. So as you can see, so we just take the values of Vin minus V2 over Rin, so which is In, and V2 minus Vout over Rf, so which is Rf. So we just put back the value of V2, so we get Vin over Rin and negative Vout over Rf. So we just switch the places of the parameters, and we get the formula for the closed loop gain, which is Vout over Vin equal to negative Rf over Rin. So next question 4, construct a summing amplifier and summarize the theory of operation. So this is a summing amplifier. So the theory of operation for summing amplifier is simple. Summing amplifier is an amplifier that adds up the value of V1 and V2 for this scenario, and times with the gain. There are different types of gain, so later on I'll show you. So after we sum, the Vout will be the sum of V1 and V2 times with its own gain. So there are three types of summing amplifier. So unity gain, average gain, and scaling sum amplifier, which is also known as scaling adder. So for unity gain summing amplifier, so unity gain summing amplifier is simple. So we have RF with 10 kilo ohm, and R1 and R2 is also with 10 kilo ohm. So we can assume the gain of this the amplifier is -1 because the value of RF and the other resistors are the same. So the gain will be -1. That's why we put negative here. So next we just add up V1 and V2. So as you can see, for 1 volt and 3 volts, so 1 volt and 3 volts, we get -4 volts because it's inverting amplifier. So that's why we get -4. So next is average gain summing. So average gain summing means that the RF is different from the R here. So here is 20 kilo ohm, and for both of the R here is 10 kilo ohm. So for this one, we just calculate the average gain. So negative RF over R times with the sum of the voltage in of the both voltage in, so which is 3 and 1. So this is 4. Negative RF over R should be -2 because 20k over 10k, so which is -2. So -2 times 4 we will get -8. So that's the way of average gain. So next is scaling summing amplifier. So scaling summing amplifier is when all the resistors are different value. So RF is 10 kilo and CR1 is 5 kilo and R2 is 8 kilo. So we have to find the gain for each voltage. So here has a different gain, and here also have a different gain. So we calculate first. So we get RF over R1. So we get 10 over 5, so we get 2. So times with 1, so we get 2. So here is 2 plus with 10 over 8 times 3, so which we will get around 3.75. So 2 plus 3.75, and so negative because inverting. So we get 5.75, -5.75 for the waveform output, for the voltage output for the summing scaling amplifier. So I think that's all for my CAA presentation. So thank you very much for listening.